In fact, because of fxy is equal to fyx, I can guarantee my second order derivative as a matrix is always symmetric, all right? This is always symmetric because these two terms are always equal. So I can easily determine whether a matrix is positive or negative. If it is positive, then your surface has to be convex. If it is negative, the surface has to be concave. But there are some other examples we'll discuss in the future. So a couple of more practices, and then the partial derivatives will be pretty much kind of in terms of computation, okay? So let's see, I have a function fxy is equal to 4x to 8, y to 5, plus 6x to 4, y to 7, okay? So I want to compute the second order derivatives and another manual. So you want to go first order first, okay? So partial f partial x equal to 32 x 7 y 5, all right? Am I writing it too small? Okay. So plus 24 x cubed y 7, okay? So partial f partial y is equal to 20 x to 8 y to 4 plus 42 x to 4 y to 6. So these polynomials are pretty easy to check. So next I want to do partial square f partial x squared is equal to so if you are not clear about what we're doing here, we're taking the derivative with respect to x on the first order derivative with respect to x. So you're looking at this function and taking derivatives with respect to x. So it's going to be equal to 7 multiplied by 24. So what I have 224. 224 x to 6 y to 5, and then plus 32 x squared y to 7, all right? And next, I want to compute the partial derivative with respect to x first and y next, okay? 160 x 7 y to 4 plus 7 to this guy. I have 168 x to 3 and y to 6. So we're dealing with large numbers finally in this class. Relatively large numbers, still within 3 digits. I'm not very confident about these numbers. You can do this twice, but you can also check your answer by taking the other way. All right? You can in fact check this answer by taking derivatives in a different order. Unfortunately for this guy, if you're not sure about the answer, you have to do it twice. But for this intermediate derivatives, x and y, you can do it in a different order to verify you actually have the right answer. So let's do that. So I'm taking derivative with respect to x about this function.
160.
So 160 x to 7, y to 4, plus I'm bringing down a 4, so it's going to be 168. So 168 x to 3 and y to 6. Oh yeah, we have the same answer, right? We have the same answer. You have to think about this. Even though this theorem is not very involved, but it is quite interesting to think of. Because even for the simplest example, polynomials, you're taking the derivatives twice with completely different polynomials at all, right? And amazingly, in the end, it doesn't really matter. You arrive at the same answer for second-order derivatives. How could this happen? Okay. How could this happen? You can think about this. And fortunately, in Calc 3 class, I don't tell you why. I only tell you how to use them. Okay. If you want to go further and study more, especially if you're interested in mathematics, computation will be not our main focus. You'll be why mathematics in a certain way. Anyway, so let's finish our computation by the very last bit of the second order derivative. Yep. Which one? This one? Okay, so this one I'm taking derivative with respect to y first. I'm getting this function. All right? Are you with me? And then second order derivative with respect to y first and x second means I'm looking at this function and taking derivative with respect to x. Are you with me? So that's why y will become constant throughout the computation in the second step. I'm break down on 8, I'm getting 160. X goes down by 1. That's what I have. Y is constant, so I keep it. And similarly here as well. So I'm bringing down 4, I'm getting a 168. X goes down by 1, and y constant, so I keep it. Right? So in each step, no matter you're doing first order derivative, second order stuff, in each step alone, it is just a single variable calculus. Okay? So even though you're doing a second order derivative, but you're essentially just a single variable calculus. So very last one. So I'm bringing down a 4, so I have a 18, x to 8, y to 3, plus 252, x to 4, and y to 5. Okay? So essentially, I have a 2x2 matrix, and I compare the anti-diagonal entries. They're still equal. So this is still a symmetric matrix. Okay? So very last one I will do, and then I will let it go. So let's do fxy is equal to y cubed sine of 3x. Okay? So I want to compute all the second order derivatives. So I'm at, what's your name again?
Joe? Joseph?
Joseph, okay.
Oh, so, yeah.
People are coming you to leave earlier.
No. it's
Oh,
That's
okay.
too much pressure then. So partial f, partial
yeah,
x,
okay, so it's cosine, 3 cosine 3x.
3y,
Okay, 3y cubed
cosine
3x.
3x. Even though I'm joking, but at least computations are easier. Doesn't mean you can always do it correctly. Okay, so there are a lot of silly mistakes I see throughout the years. People are so confident about their single variable calculus skills, and they are computing the partial derivatives. They forget one is constant, they forget the other one, you have to bring it down, everything. Yep.
So for the second order derivative,
Mhm.
we can't know whether it's concave up or down unless we have the points to calculate the matrix.
Yeah, exactly. So the convexity and the concavity, you have to evaluate these metrics at a given point. So we were talking about the point, whether you can achieve the maximum where it is convex. You can achieve the minimum if it is concave. I think it should be the other way around. But anyway, and also you have a saddle point. We will go there eventually, okay? So partial f, partial y. What do you have?
3y squared sine 3x
3x.
plus y cubed cosine 3x.
No, this is a constant.
Why am I doing anything?
Oh, wait. Oh, that's right, yeah.
Right? So x is
Yeah.
constant. This whole sign thing is just a constant coefficient,
Yeah.
right?
Yeah.
Okay? So you still have to be pretty careful. So partial f, partial x squared. So I'm taking the derivative of this guy twice. So I'm taking the derivative with respect to x.
So that would just be, that'd be 3y cubed
3y cubed
will be negative 2.
negative sine
Negative sine
3x, but I need to
times 3, yeah.
times 3, so it's minus
9.
9. Okay, so minus 9y cubed sine 3x. Okay, so partial square f partial y, partial x is to take derivative with respect to y for this partial derivative. You're getting a
Be 9y
9y squared
cosine 3x.
3x. Okay? And next one is partial square f, partial x, partial y. So y and the x second.
Okay, so that would just be, will that be constant to be 3y?
3y squared keeps down
Cosine, that would be, yeah,
cosine 3x, and then
times 3,
with
yeah.
times 3, so it's going to be 9y squared. So I checked for polynomials, I also checked for trigonometric functions. For trigonometric functions, the second order derivative with interchange variables is still equal. The order doesn't matter, okay? And very last one, partial squared f, partial y squared is going to be equal to,
It'd be,
so I'm looking at this
yeah,
and taking derivative with respect to y. So we are having,
hold on.
so this whole thing is constant, right?
Okay, yeah, so that's a constant. So there'd just be 9y. Wait, no, 6y.
Sine 3x.
9y.
Okay, so here is what I learned from you guys. You guys are all pretty good at the single variable calculus, but you do have to practice a lot. You have to practice and get your brain programmed. So every time it is like a reflective. Everything about the partial derivatives, it can immediately filter out all the other variables and concentrate on the one which you are taking derivative of and quickly get the partial derivative. Listen to me carefully here. So this class is not about how much you know mathematics, it's about how well you know. So it is a skill test. In the end, and in the test and in the final, they will throw at you a lot of questions. You have to be able to do those questions quickly and correctly. So you have to practice. You have to practice through more and more computations. And the rules are pretty simple. Next class, we have to discuss one more thing. Okay, we'll discuss one more thing. So we are applying all the single variable calculus rules when we compute partial derivatives, especially about the product rule, quotient rule, and chain rule. The product rule and the quotient rule are still the same for partial derivatives. Doesn't change at all. But the chain rule is actually more diverse. We'll have a discussion about chain rule in multivariable calculus in its specific form in next week. So keep doing this online homework and let me know how it works out in the end.